What will a warming Arctic do to rivers? What impact will a warming Arctic have on river flows? Hello, friends. Jim here. Well, this article appeared on phys.org, and there's a couple of scientists that are working to figure out this question. We know the Arctic is warming. What will changing rivers flows do to its environment? Okay, here's the gentleman leading the research for the last 20-something years, Michael Rollins from the University of Massachusetts, Amherst. And based on satellite imagery, direct field observations, numerical modeling, they're trying to ascertain the changing Arctic landscape for the next 80 years or so. Overall, the region will be warmer and wetter, but the details: up to 25% more runoff, 30% more subsurface runoff, and a progressively drier southern Arctic provides clear assessments on how the landscape will respond to the changing climate. Their results were published in the journal The Cryosphere. Arctic is defined by the presence of permafrost, a permanently frozen layer on or under the Earth's surface. It's that permafrost that drives everything from seasonal runoff through the freshwater dumping into coastal lagoons to the amounts of soil carbon that wind up flowing into the ocean. Because if you've got permafrost, that's frozen ground. Water, any precipitation that's moving through the active layer, the part that's thawed out, when it hits that permanently frozen layer, it's a barrier. The water or precipitation, whatever it is not able to penetrate any further, and therefore then starts to move horizontally, where it can be discharged, put back into oceans, and or make its way into rivers or to the surface and evaporate. So they're looking at what this happens. And just as I did a video about how rain is working its way through the permafrost here in the Fairbanks area, that's adding to the thawing of the permafrost and hence release of CO2 and methane. Well, basically they're looking at how does the thawing permafrost, how does that impact rivers? So they're looking at that aspect of it. The Arctic is warming 2.5 to 4 times, sometimes 5 times faster in certain places than the global average, means that massive amounts of carbon-rich soils in permafrost regions are thawing, releasing their carbon in the form of CO2 and methane typically to rivers in the atmosphere every year. The thawing is also intensifying the Arctic's water cycle, which is, the precipitation, the runoff, evaporation, etc., that determines the region's environment. The upper part of the permafrost that thaws each summer is called the active layer. And this is the layer that's been of interest to Michael Rollins, who's an associate professor at the Department of Earth Geographic and Climate Science at UMass Amherst, lead author and researcher. As the Arctic warms, the active layer is getting thicker, meaning going deeper. And Rollins wants to know how that thickening, combined with warming and an intensified water cycle, would affect the terrestrial Arctic environment. So he spent 20 years doing this stuff, refining his permafrost water balance model, which accounts for seasonal thawing and freezing, runoff, etc., etc. So he teamed up with the U.S. NSF, U.S. Department of Energy, NASA, and Ambarish Kamalkar, a research assistant professor at UMass Amherst, where he basically completed his doctorate, and he's now over at the University of Rhode Island. I will go over this diagram in a bit. It's very interesting. So Kamakar is an expert in the use of global climate models, and he and Rollins use precipitation temperature scenarios to figure out or explore different possibilities. What might happen in the future? For example, a moderate case in which greenhouse gas emissions and therefore global temperatures are curbed, and a high emissions and warming scenario. Well, don't forget the lag effect, pipeline warming and so on, and we already got certain warming already locked into place. So hopefully they took that into account. So they kind of crunched some numbers, and what they found is the following. A thicker active layer creates a bigger bucket for storing water. Will make sense. If the ground is not frozen, then water will percolate there and be stored there. Our work shows that as precipitation intensifies, the water will be stored longer in thawed soils and released at a later time via subsurface pathways instead of running off immediately into rivers and streams as much of it does now. The study demonstrates how thawing soils will increase runoff to rivers in fall because the ground won't freeze as early in a warmer world, whereas before it would run off earlier in the year. Between now and 2100, the yearly proportion of subsurface runoff will increase by up to 30%. Moreover, this increased runoff will happen mainly in the northern parts of the Arctic. Some of the additional water will originate from evaporation caused by an increasingly ice-free Arctic Ocean. Southern portions of the Arctic will warm so much that evaporation and plant transpiration, right, that's water loss out the stomata, will send much of the additional precipitation back to the atmosphere, resulting in an overall drying out of the landscape. Now, you have heard me say that as air warms, it can hold more moisture, and it's going to do what? Suck the moisture out of the ground. Well, that's basically what they're saying right here. And toss in more, pulling out more moisture out the plant stomata. All this has a number of implications for the Arctic. Northern rivers, especially the regions largest, the Ob, the Yenisei, the Lena, and the Mackenzie. Okay, the first three over on the Russian side, the Eurasian side. We'll see proportionally more water coming from their northern reaches. Because there's more soil carbon in the northern Arctic, it is likely that more of it, some frozen for thousands of years, will wind up flowing through rivers to the Arctic Ocean. In other words, they're thawing out, and the carbon gets transported by the water to the Arctic Ocean. Now, leads to an interesting point. You introduce all this carbon. Will that help producers? The increased discharge will affect the dynamics of coastal sea ice, change the ecology of the biodiverse Arctic lagoons, and affect ocean freshwater storage, potentially slowing AMOC. Now, when I had discussed what's happening before with AMOC, one of the things I have mentioned is the increased river discharge. And the Beaufort Gyre, which is a clockwise gyre that has a convergence zone in the middle, will actually concentrate this freshwater buildup. You get a doming. Now, some of it may through via Ekman downwelling, Ekman pumping. Some of that can be moved to deeper depths, but it could very well stay up, causing increased stratification. And depending on what the Arctic dipole is doing, will either constrain that within the Arctic Ocean or push it out through Fram, impacting our good friend AMOC. So, another example how everything is tied together. You're changing the groundwater, you're changing the discharge. In some cases, you are storing it longer. Other cases, you're pushing it out sooner. Or what gets stored longer will eventually be pushed out. And a lot of that's due to increased precipitation. The increased precipitation resulting from the increased evaporation due to sea ice loss. So let's take a look at these diagrams. And it's a little hard to read some of the figures here. For example, I think it says CO2. I really don't, it's too blurry here. But what the top two panels show is the change in the annual total runoff, and then the change in the fraction of the subsurface runoff. So they're looking at from basically they're projecting out to 2080 to 2099, but they removed the signal from 2000 to 2019 in both panels. So the blue shows a reduction in runoff. The red to dark brown shows an increase in the runoff. What did they say? They say that the southern Arctic, because the permafrost is thawing, the active layer is getting thicker, it can store more water. That is exactly what we're seeing here in the blue. This is showing the water being stored. And here we have the increased runoff because, well, sea ice is here. Well, the ocean is here. You're losing the sea ice, more precipitation. It falls here and then, well, pours it back in there. So what you're doing, to think about it, let's say you have a certain uniform salinity here in the upper 50 meters or so. Now, because sunlight evaporating, you've now changed the salinity of the upper, say, 5 to 10 meters. And then you've increased the salinity of the lower 40 meters. Because you've done what? You've taken the freshwater component out, moved it into the atmosphere, it comes down precipitation, then runs off. And now you have freshwater land. There may be some mixing, so you can entrain that, through double diffusive mechanisms and so forth. But you're changing the salinity profile. So that's what we see going on here. And, and to a certain extent, the same thing here. The subsurface, because the active layer is deeper and thicker, it can hold more water, less of it will run off. So that's what they're showing here. And the bottom two panels show the accumulated river discharge during early and late century periods, and then the soil organic carbon storage. Well, the discharge here, again, I really can't make out what these are here, but the units are on the vertical axis is a river discharge in cubic kilometers per year, and they're going by latitude here, so 45 up to 75. And what we see here is a very clear trend of increasing volumetric discharge. So more water is being, which then, impacts, as I discussed earlier, like, for example, the Beaufort Gyre. Does the fresh water stay here, or does it get pushed out to Fram into the AMOC region and so forth? And this is the soil organic carbon, which is given as kilograms per square meter. And again, the horizontal axis from 45 to 75 degrees north latitude, and increasing range here. And you'll see that the storage overall reach. I think I know what this is. This is the Obe River, the Yenisei, the Mackenzie. Okay, these are the different rivers here. Okay, that's what these are. So the black is the Obe, and you can see the storage is highest around 63 north latitude or so, where the Mackenzie, it's almost near 70 degrees, like 69, 70 degrees, where it peaks out. So this shows very nicely what they're saying, that the discharge is going to be higher in the northern Arctic, but because of the increasing thickness of the active layer, it's going to store more water. And therefore, when it starts with more water, you're going to start releasing more carbon. And that's reflected, for example, in the Obe River and so forth. So, interesting findings here. We'll have to stay tuned to see what their future work reveals. So, until next time.